investing money. So there's these things called annuities. And so it uses compound interest for your investments, but rather than just making one investment with an annuity, you're making regular investments. Now, it's called an annuity, I guess, because originally it was every year, so annually it would happen. Now, different types of annuities. Ordinary annuity is when you're paying the same amount at the end of the compounding period, whereas annuity due is when you deposit the same amount at the beginning of the compounding period. So annuity due is more your investment, ordinary annuity is more your loan or something like that. Future value is the total value of that investment at the end of the whatever the term is, however many years or months or whatever it is you're doing it for. Present value. Now that is, look, instead of paying regular amounts, what about if I just paid one amount at the start? Now obviously I've got to put in more money, but if I did that, what is that amount that would give me the same amount as over the future? And by the way, just to make it really confusing, there are financial products on the market called annuities. They just call it an annuity. It's just one type of annuity. Now, and there are other types of annuities, so it gets confusing because you can say, you can have an annuity which is not an annuity. I know, weird. All right, let's look at this annuity due. Superannuation fund's a good example. Pays an interest rate of 8.75%. That's not a bad rate. We're going to invest $5,000 at the beginning of each year. So how much is it going to be worth when she retires in how many years' time is that? Is it 21 or 20? Because you've gone all of 2003. Yeah, you're right. Because you've gone all of 2023, haven't you? So there we go. So that very first amount that we put in would be invested for 21 years. The second amount would be in there for 20 years. And so on until we get to the last amount, which will just sit in there for a year. So if we want to work out the total amount, what we'll basically end up with, because of the similarity between compound interest formula and a geometric series, that's what we've got. A sum of 21 terms. So for this one, our first term is 5,000 times 1.0875. R is 1.0875, and the number of terms is 21. So sum to 21, plug it in our formula, and there we go. We've got $299,604.86. Well, when will it first exceed 200,000 then? Okay, so there's our sum. The difference is now we don't know how many years. When is sum to n greater than 200,000? Same formula, but now we've got to find n. Calculator work really, and then eventually we come down to, there it is, log both sides, divide by the log of 1.0875, but of course, that's a positive number, good. So we don't change the sign. So 17.1, 18 years. So at 17 years it hasn't happened yet, so 18 years. So 2021. Let's go for $1 million. Everyone likes that figure, $1 million. So what annual instalment would have produced $1 million? So this time we just don't know what the principal is. We're saying how much should I put in each time to get $1 million? So my sum to 18 will be $1 million. And now it's just making P the subject of the formula. And calculator work, $22,818. Remember, that's each year. It's not like every week you've got to get in your pocket and do that. So that would produce $1 million. I guess the key to these questions is the original setup. How you can get to that geometric series. Once you've got the geometric series, it's just like the problems we were doing yesterday. It's solving a geometric one. Okay, so future value of an annuity due. So the future value will be the sum to n terms. Now you can't actually quote that formula. You've got to set it up and create the series. But basically that's what it is, isn't it? The future value is the sum of all those terms. P is our principal, R is our interest rate, and N is our time period. So if Stephanie could afford it, how much money could she save by making one single investment and still have the same future value in 21 years' time? So we're saying it's now just one compound interest. So the present value but it'll be there for 21 years, and we want to get it to the same answer we got in that first question, wasn't it? Which came out to be $299,604.86. So divide by the 1.0875. So if she could afford it, by just simply plonking down $54,500 now and doing nothing else, in 21 years' time, she'd still have the same amount of money. How much would she save? Well, because what she ended up doing was placing $5,000 down for 21 years. So had she done it the other way, she'd end up paying out $105,000. So she'd end up saving $50,532 by doing it that way. So that's why you might consider doing something like that, if you could afford it. So the present value of an annuity due. Present value times R to the power of n, that's got to equal our future value. So we could create a formula for that. But again, you can't quote the formula, but that would be one for present value, where P is principal, R is the interest rate, and so on. Sometimes they just ask you to read off a table. So rather than doing all the calculations, so Tim and Janine offered 6% per annum for 4 years. Tim invests $1,500 each quarter, compounded quarterly. Janine, $500 every month. Who earned the most interest? That's just a matter of reading off the table. So Tim, 6%, that's the same as 1.5% per quarter. So that's where we're looking for, because there would be 16 quarters. So we get 17.9324. But times the $1,500 investment, 26,898.6. Well, Janine's 6%, she's doing 0.5% per month, but that would be for 48 months. So hers is 54.0978. Times that by 500, because her investment's 500, ends up with 27,040. So Tim's interest, we've got to take away the actual investment. He made 16 payments of $1,500, or investments of $1,500. Tim's made $2,898.60. Janine made 48 investments of $500. Her interest was $3,048.90. So Janine ended up with the most interest, just by $150. Okay, all of that for 5 questions. There we go.